Okay, so question 4. The question is about an initial motor of a boat and trailer and pull up a ramp as shown in figure 1. You can see the boat and trailer here obviously getting pulled up the ramp. The boat and the trailer are pulled by a motor which is connected to a 24-volt battery of negligible internal resistance. Okay, nice indication there. We're not going to be doing anything with internal resistance. The motor is switched on at time t0. Figure 2 shows the current in the motor circuit varies with time. So you can see here there's a surge and then obviously it drops off. So what we're getting asked, determine the total energy input by the 24-volt battery to the motor in the first 200 milliseconds. Okay, so what you're going to want to do here is you're going to want to think about what equations can I use to get what I want here. And do you remember I've said quite a few times, reinforce this loads of times, when you are looking at a graph, it is going to be more often than not, pretty much every time, it's going to be either gradient, reciprocal of the gradient, or area. Okay, so you need to look at y and x and what happens. Okay, so if you get current over time, okay, you need to think about what you're going to get. That's your gradient, right? And if you get current times time, what are you going to get? Okay, well, current times time is going to be charge, because Q equals IT, right? And therefore we can think about that in terms of the question and see if it applies. So determine the total energy input when 24-volt battery is applied. So what do I have with energy? Do I have anything with energy, what I get for the gradient and voltage? Do I have anything with energy, what I get for the area and voltage? And we do have energy, charge and voltage, right? Because voltage, by definition, is going to be equal to the work done per unit charge. Okay, so we can rearrange that and we can say, well, V Q is going to be E. Okay, if we're going to get that total energy from that point, we need to figure out how we're going to get it from the graph. And again, I've said this many times, don't waste time on graphs like this doing complicated things. Okay, you're not going to be asked to do that in A-level physics. I saw a few of you trying to work the geometry, okay, trying to think of this as a triangle. That's fine, because it's going to give you a sort of an allowance for something like this, right, for counting the area. But mostly what you're going to do is you're going to need to count the squares, right? That's basically what you're going to be doing here. So we're going to think about, well, we've got 30 and we're doing this within the first 200. So it's this section here, right? So 30 to 200 there, okay? So do this in seconds, okay? So the equation works and I get joules, okay? So 30 times 200 times 10 to the -3, and that's going to give me this, how much charge is contributed in that part of the area under the graph. And then I need this one, and for this I'm just going to think about, well, I'm just going to count the squares. And generally speaking, what you want to do is you count the squares with more than half, and that'll account for the squares you haven't counted with less than half, okay, and give you a balance. So you can see each one here is 10 to 25, so each square 10 times 25 times 10 to -3, okay, which means then I just need to count the squares, multiply it by that, and add on what I've worked out here for this section. So here we're going to count 1, 2, 3, and remember I'm just counting the ones where I can see more than half. 4, I count that one, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so I've counted 17 total squares. Obviously some of these aren't full squares, but the gaps there are accounted for by these areas I haven't counted. Right, you can see obviously there's a lot of area that I haven't counted. But that's why it gives you a bit of leeway, right? So let's have a look here. 16 times. Okay, so just having to do this on my iPad, bear with me, because I am using my phone to record. So times 10 to the negative 3. Okay, so for that one, I'm getting 4, and then okay, 10. Okay, so I am getting 4 as a result of these. So I'm getting 30 times 200 times 10 to the negative 3. I'm getting that to equal 6. Okay, so that is 6 coulombs of charge from that. 10 times 25 times 10 to the negative 3, which is what each of these squares is worth. I'm getting to be 0.25, and then if I multiply that by the total number of squares, 16, I'm getting 4. So that's 0.25. 0.25 times 16, which is my squares, equals 4 coulombs. Obviously adding those together, total 10 coulombs. Okay, so let's go back here. Work done, the total energy is voltage multiplied by charge. So Q equals 10 coulombs. Voltage is 24. So my total joules is 240 joules. Okay. Now you can do that with a bit of leniency. It's going to accept answers in the range of 220 to 264. But that's the way you want to do it, right? You want to think about these squares. Okay, I did see some of this, well done if you did do that, but that's how you're going to use graphs. Don't forget, think about gradient, think about area. So the boat and the trailer are initially at rest. In the first 200 milliseconds, the boat and the trailer are raised through a vertical height of 3.3 times 10 to the negative 2 meters, and the speed increased to 0.85 meters per second. Assume that all useful energy output by the motor is transferred into kinetic energy and gravitational potential energy of the boat and trailer. So we're going to say all useful, that's all the useful energy. Okay, so anything that's left over is considered wasted energy. Okay, so the boat and trailer have a total mass of 180 kilograms. Determine the average efficiency of the boat through those first 200 milliseconds. Okay, so first off, we're going to need to think about, we've got our total. Right, so we need to think about how we're going to get to the efficiency, and the efficiency is, remember, the useful out over total in. So the total in is 240. So the useful out is going to be a combination of these two things. It's saying that our usefuls are the kinetic and the gravitational potential energy. So the useful out is going to be, let's do kinetic energy first. It's gone from rest to a speed of 0.85. So obviously that's going to be half mv squared, which is 0.5 times the mass, 180, times 0.85 squared. Okay, and then that gives us .65 joules of total kinetic energy, The gravitational potential energy is the other useful store. Okay, so what have we done? We've gone up by 3.3 times 10 to the negative 2 meters through vertical heights. That's the height we're going to use, not the height of the ramp itself. So if you look at this, we wouldn't use this height, okay, for distance of gravitational potential energy difference. We would use this one as our delta H, right? So we can use mgh or mg delta H, okay, where the mass and gravity are of course constant because we are close to the Earth's surface and not moving through changing potential. So 180 kilograms multiplied by 9.81 multiplied by change in height 3.3 times 10 to the negative 2. Okay, so let's just do that. 3.3 times 10 to the negative 2. So I'm getting 58 joules, or 58.3. Okay, so 58 joules. So total useful input is going to be these two combined, right? So obviously 65 plus 58. So our total useful input is going to be 123 joules. So if we put 1, 2, 3 there, do 1, 2, 3 over 240. That should give us 0.51, hopefully. Yeah, 0.51. Okay, and then we're going to multiply that by 100%, sorry, to make it a percentage if we're going to give it that way, okay? So unless it asks for a percentage or gives you a set unit, you can give either. So I can either put 0.51, or if I want to multiply by 100, I can put 51 and clarify with a percent symbol, okay? Just if you do obviously do that, make sure you clarify that it is a percentage. Right, so this last one here now, either of the circuits shown in figure 3A or 3B could use the reduced initial could be used to reduce the initial current surge. The thermistor and the fixed resistor have the same resistance when they are at the temperature of their surroundings. When the surge is ended, the boat and the trailer continue to move at constant speed to the top of the ramp. Explain, with reference to the properties of the thermistor and the fixed resistor, why using the thermistor is preferable to using the fixed resistor. So the idea here is to reduce the initial current surge, okay, and to, if there is an initial current surge, it's also going to be to allow less energy to be wasted, right? And how can all that happen as a part of this circuit? So first thing is going to be establishing what the problem is, right? What do you, some of you explain the difference in the properties, but you need to recognize the problem as well. So I'll give you the example, right? So a lot of people said, make sure you get this right around, because a lot of people actually got this the wrong way around, right? Most objects, like for example, this standard fixed resistor, or we looked at obviously things like light bulbs, as the temperature goes up, the resistance is going to go up, right, because of the particle movement. However, in a thermistor, as the temperature goes up, the resistance is going to go down. So you've got to remember that's the other way, right? Same with a light dependent resistor. As the light intensity goes up, the resistance will go down. So as thermistor, you're going to say you can say this in a bit more clear way. I'm just doing this to be quick. So thermistor equals resistance up, temp up, resistance down. Okay. Now the thing is here, you can say this and you can get right into talking about the properties of these and how the resistance here isn't going to change, right? But the problem you have is you haven't explained why that's a problem. Does everyone see that? So you thermistor temperature up, yes, this is great, but it doesn't actually say, I don't believe, that temperature is the problem. Right, losing energy to that temperature is the problem. No, it just tells you there's a current surge. You're aware there's going to be a temperature increase because of the current, but you need to state that, okay? So you need to say that heating is going to occur. Heating occurs due to current surge. And then thermistor, unlike the resistor, I would compare that to the other, the fixed resistor. Fixed R remains high. Remains high resistance. Heating occurs due to the current surge. And then I'm going to say, well, what is the benefit of the resistance going down? And if there's a low resistance for the thermistor, it means less wasted power, right? Because P equals I squared R. Okay, so if I is going to increase hugely, you want to drop R to reduce the transfer of energy. Okay, you're kind of trying to reduce the lost energy here, right? So you're going to say, therefore, low resistance. Don't forget to tie your points together, okay? Low resistance, therefore, means less wasted power. Okay, so make sure you go on to the next, to next, to next. Okay, so that's 3 marks. One's going to be for saying that heating occurs, one's going to be for explaining the difference between the two, and one's going to be telling you the benefit of what that difference could bring.